Good afternoon. Last time we established a basic way of describing risk as basically an outcome associated with a likelihood. It allows us to have a formal way of describing, calculating risk in an objective rather than a subjective approach. We came into the point where we tried to identify when is it that risk exists, and we made the point that risk exists only on an anonymous basis. It exists also in terms of the existence of uncertainty, and so these are conditions for any estimation of the risk, and we defined that we can describe risk as either a probability distribution when you have discrete variables. I gave you that as a simple assignment, or as a probability density function when we have a continuous function to describe. Again, risk is associated with the existence of uncertainty in both the likelihood, as well as the outcome from the different whatever we are looking at. The victims of risk, for us to call it risk, must be anonymous. You cannot identify a person and then subject them to some undesirable type of an event and then say, oh, it is he was subject to risk. If you choose a particular person and he is subjected to some risky behavior for one reason or the other, then it becomes a crime. And our ethics and our professionalism does not allow us to do that in general. The third condition for the existence of risk is that it is a prediction process before realization. You can call it an anticipatory process. Once the undesirable event that we are dealing with does not exist anymore, risk disappears. It's not there anymore. If, say, we say that there is a risk in taking an airplane, takes risk of accidents, well, it is a risk. We calculate it and we act on it. But if, say, God forbid, the airplane has an accident, there is no risk that exists anymore. So it's a predictive process or an anticipatory process. Risk is also associated with what we call meta-uncertainty. So you'll find that the risk profile that we defined last time as being the farmer's curve, which is the complementary cumulative distribution function, is associated with uncertainty both on the outcome as well as the likelihood of the accident. So we call this a meta-uncertainties. The range of uncertainty can span in some risk estimates maybe 3 orders of magnitude. And basically you have error bands, and they can be uncertainty associated with the outcome levels or uncertainty in the frequencies of the likelihood. The existence of meta-uncertainty makes risk management or decision-making under uncertainty very difficult. It's not an easy task to do, and controversial in terms of engineers and scientists having the task of convincing the public that they made an appropriate estimation of the risk. So here we have 2 types of risk. What we are doing in our course, obviously, is what we call risk assessment. We try to estimate the risk, what is the level of risk that is acceptable in different design projects. And here I go back to what we call the farmer's curve. The farmer's curve described to us the annual frequency of fatalities exceeding the number X here for different events that happen from technology. Air, actually also, yeah, it is fires, air crashes, explosions, dam failures, air crashes, person on the ground, chlorine releases. So here we have 100 nuclear power stations, and definitely the risk in terms of the number of fatalities, say, exceeding maybe here, if that's 1,000 or 5,000, is way or 3 orders of magnitude below any type of other accidents that we encounter in society, like air crashes and fires. So in that case, we can say that, oh, it is an acceptable risk. We live with the design features of existing nuclear power plants. If your 100 nuclear power plants had a risk that exceeds any of these other activities that are acceptable in society, then the risk is unacceptable. And in that case, we'll have to go and back to the drawing board and redesign our nuclear power plants in such a way that the risks from operating them does not exceed other acceptable risk in society. Notice that the farmer's curve that we have shown here is identified as the complementary cumulative distribution function of the probability density function that we agreed would describe the risk in an objective, not just a perceptive way. I want to make a differentiation between the processes of risk assessment that we are going to become experts in doing and risk management. You'll find as an example of risk assessment is what we are going to designate or call probabilistic risk assessment for nuclear power plants. You can apply that to any other engineering aspects or activities in society. And the process of risk assessment, as we learn, as we go along, includes the enumeration of the sequence of events that could lead, say, to a meltdown of the core. That's happened in the 3 Mile Island, it happened at Chernobyl, and it happened at Fukushima. Then we have to clarify the containment structure. We have engineered safety features protecting the plant. We would like to identify what are the modes by which the failure can occur. We want to estimate their probabilities and timings. We want to identify of the quantity of the chemical form of the radioactivity release if the containment is breached. We call this a source term, and we are going to have a whole chapter on that topic. Then we have to model the dispersion of the radioactive nuclide in the atmosphere. Then we model the emergency response effectiveness involving sheltering people and maybe not just sheltering them, but also moving them away from the radiation area that has been contaminated. Then we talk about the evacuation and the medical treatment. Then we describe a response to their being affected by radiation. And it could be a chemical plant, it could be a hurricane, flooding, like flooding is happening all over the world. And you estimate basically the health effects on the population exposed. So a natural disaster can start like flooding, but then if the water supply is affected, then you can get other secondary effects like the spread of waterborne diseases like cholera in that case. So this is a process of risk assessment. On the other hand, when we talk about risk management, this is a different game. It goes beyond risk assessment only. And in that case, you start proposing alternatives. For each alternative, you evaluate the risk profile, that farmer curve or the complementary cumulative distribution function. You make safety decisions, you choose satisfactory alternatives to control the risk, and you exercise corrective actions. So in that case, it becomes the realm of more or less system analysis and operations research, rather than the realm of applying probability theory and possibility theory. Risk assessment is a scientific approach. Risk management involves value judgment. Risk assessment is a technical approach. Risk management uses heuristics. Heuristics is another way of using rules of thumb, like basically rules that you write the technical specification of any engineering device. Risk assessment is formal. Risk management is subjective. Harder, of course, to deal with subjective matter, whether you are having something that is objective or formal. Risk assessment is quantitative. You quantify the risk. Risk management is qualitative. Risk assessment definitely is objective because we are going to get numbers that represents the level of risk. Risk management includes political and societal decisions in general. If you couple both risk assessment and risk management, this is basically a field of science designated as risk assessment and management. And it is not just PRA, like what we are going to try to learn, but it's PRAM. You add the letter M into the acronym. Would you please pass around an attendance sheet? This is in essence what we'd like to do today for the risk assessment methodology. We have already learned about the concept of the safety indices. We suggested the scale that goes from 0 to 10. And that is a way to a certain, we can say that is a way of estimating risk and assess, allocating to it a value from 0 to 10. Same as the Richter scale that exists there, the Torino scale, that are all used in the estimation of what is the level of damage that can happen from different phenomena, earthquakes in particular, the Richter scale, the Torino scale, and the Fujita scale for tornadoes and so on. I'm going to jump ahead because we have already learned one method of risk assessment here into another method of risk assessment. And that other method of risk assessment doesn't need the basic axiomatic approach of probability theory and possibility theory, Boolean algebra, and the Morgan algebra that we are going to use to develop these other methodologies. This methodology is a methodology that's adopted from the field of economics. And in economics, you all heard about the concept of cost effectiveness. So what is cost effectiveness? If you are studying only economics, not risk assessment, this is synonymous with what is called in the field of economics, a marginal cost benefit analysis. So if you want to learn more about it, you go and delve into the literature in the field of economics. It tries to estimate for any kind of activity or a design how in a way the cost of reducing the risk against the benefits that we get from reducing the risk. And again, as I told you, risk can be monetized. It can have a monetary value, and that's why the economists would deal with it, not just the engineers or physicists in that case. You'll find that cost effectiveness analysis answers the question or whether or not a given technology or a, or a given design should be made safer more than what it really is safer by the addition of extra safety equipment. And obviously, if you add extra safety equipment, you will have an extra cost. It will cost us more to add the safety equipment. Hence, it will cost us more to reduce the level of risk if it is not acceptable to us, but not to us as engineers. As engineers here, we are servants to society in general. If society requires us to reduce the level of risk, we have basically to use our skills and our knowledge and our education to reduce the risk. So cost-effective analysis comprises an array of other methods of risk assessment, like the comparison of risks and benefits, where a set of alternatives may be used to choose among different options. And this requires the risks and benefit to be expressed in the same units. So we have to be careful here. What are the units that you use to express the risk? It also involves placing the risk into perspective. with the objective of determining whether the risks of a technology compare favorably with the existing risks of presently accepted technologies. We cannot develop a technology that would have risks associated with it that exceeds what society is already accepting in that case. And we'll discuss that later on in terms of the ethics of the professional societies later on. We'll come back to that chapter later on. But for now, we are going to learn about a second method for assessing or estimating risk. The risk of any new technology, as a kind of rule of thumb here, should be at least a factor of 10 lower than well-established technology. If you do not have that simple rule of thumb criterion, it will be very hard for you to introduce a new technology into our industrial and technological society in general. So what is cost effectiveness? Well, cost effectiveness is a way of generating a relationship between a reduction in the risk for a given technology, let's call it delta R sub I, because it is not just one way that we have available to us to reduce the risk, as we'll see in a moment, but we may have different incremental values of reduction of the risk. We suggested that risk is associated with a cost to reduce the risk, and we'll take an example in a moment. It becomes more and more expensive to reduce the risk even further, for instance, from some level S sub 5 to S sub 6, and I'll go there immediately into a diagram that we call the cost effectiveness curve. And in economics, you may have seen it in your economics classes as described to you as the law of diminishing returns. If you haven't seen it in economics, we are seeing it here in the course on safety. Any engineering device or any basically activity in society, whether it's riding a bike or a motorcycle or a car or taking an airplane, involves some risk. So basically, you'll find that any engineering device has an inherent risk, as we call it, S sub 0. Okay, let's talk about a car here as an example. So a car that you ride in can get into an accident. Unfortunately, sometimes the accident is not caused by you, but by some other people. But there is always an inherent risk in any technology. Now, suppose that that level of risk, or maybe from the statistics that we get, is not acceptable to us. So we want to reduce that risk. The theory of cost effectiveness analysis tells me that I can always reduce that risk from a level S sub 0 here to a level S1, provided here we go on the x-axis and spend some money. That is the cost, delta C1, C stands for cost here, the cost of the risk reduction. And let's take an example from that I started describing last time. If you have a car, an older car, and you want to reduce risk in an accident from a level, say, S sub 0 to S1, you reduce the risk by an increment delta R1. You notice that you spend delta C1 to reduce the risk to that level. And an example that we started talking about last time is adding seat belts. And you don't think about cars today not having seat belts. And let's say let's say that you spend $200, as we started mentioning last time, to add a seat belt. Okay, so that reduces the risk by a very large amount, spending only $200. But as you keep reducing the risk, you'll find that, say, you want now to reduce the risk, let's say from S2 to S3. Let's take that example here. You'll find that to add an extra safety feature, and we suggested maybe airbags, you'll find that you'll spend a larger amount of money here. Do you see here that little amount of money with the seat belt? This is the airbag. You have to spend more money. And you can reduce the risk, say, from S2 to S3, but you notice that you are spending first more money, but the amount of risk that you reduce is less than the initial reduction of the risk. And you can go and add, say, not just driver seat airbags, but you can add the anti-lock brakes. Maybe you should actually add the anti-lock brakes before you add the airbags. Say from 200 for a seat belt to 800 to add the anti-lock brakes to 1,000 or 2,000 to reduce the risk further by the airbags. And then you add side airbags. If you buy a Lamborghini or a Mercedes or a BMW, they have also side airbags, not just, and then you can also have the camera in the back of your car. Some new models of cars even have a radar that measures the distance between you and the car in front of it, and would slow down your car if you get too close to the car in front of you. Each time you reduce the risk, you have to spend a larger and larger amount of money with a lower and lower amount of risk reduced as you spend, as the cost of risk reduction increases. In economics, this is the law of diminishing returns. You could see here that we're spending lots of money, but the risk reduced only a tiny amount. Whereas initially we reduce the risk by a large amount, spending a very little amount of money. If you haven't seen this concept of diminishing returns in economics, so you may go to Wikipedia and read more about it, but that's a very interesting concept. All right, so the law of diminishing return is a description of the risk profile, how to reduce the risk. We have to spend money. Now, let us notice something very important in that graph here. Initially, we can reduce the risk by a very large amount, spending a very little money. Maybe as I suggested, maybe the seat belts. Later on, we'll have to spend a large amount of money, but we only can decrease risk by a very tiny amount. That's a law of diminishing return. But something else appeared in that graph. In that graph, basically goes there asymptotically, it never reaches zero. Meaning what? Meaning that as we attempt to reduce risk in any kind of a technology, yes, we can reduce it by spending money, but in theory, at least here, we are never able to reduce the risk to zero. I repeat that. As engineers, we cannot reduce the risk to zero. It goes there here asymptotically up at infinity. So it's a professionally and ethically an obligation for us when we design objects or systems that are less risky, that we make them safer to society, that we have to explain to society that we cannot reduce the risk to zero, because it would imply spending an infinite amount of money, which of course negates the benefit that we get from the process of reducing risk. For instance, we cannot go and add to cars, for instance, a periscope or that looks, well, we have video cameras already, but adding more and more features would make the device that we are designing or operating much too expensive to deal with. All right, so this is the concept of the cost effectiveness curve. We cannot reduce the risk to zero, and we have to make that clear when we design objects or systems or new designs of any engineering devices, that we make it clear that yes, we are reducing the risk. We have to spend some money. Maybe the cost is very desirable because it reduces the amount of risk. It saves lives, or it could save money, or it could save injuries to people, but we cannot reduce it to zero ever. We cannot tell people, oh, we are going to design you a car that is absolutely safe. No way. All right. So this is ethics, and that we have to abide for as engineers. Now let us quantify that curve right here, the cost effectiveness curve. We quantify that by defining what we call the cost effectiveness. And the cost effectiveness is that risk reduction delta R, we are reducing the risk by spending some delta C money to reduce that risk by the amount delta R. So in that case, if we take the risk curve, this is really the inverse of the slope of the curve, because here, if you go to the back to the curve, it's delta R divided into delta C. That's the slope of the curve, right, mathematically. And we can translate that into some very simple equation, and we call it the cost-benefit ratio. So you find here that you write in the numerator the cost of reducing the risk in any kind of an engineering system, and divided by the risk reduction. Now, how do we describe the risk reduction? We take it over different ways of reducing the risk. Remember, we said, oh, we add a seat belt and anti-lock brakes and driver airbags and passenger airbags and so on. So in that case, you take the risks of the different options, sum it over the different options, and multiplied by the likelihood or the frequency of occurrence of the different incidents that you are adding those safety features for. For instance, you get statistics on, say, people being hurt by not having a seat belt on when they drive cars. And at some point, cars driven by people, and still is, in fact, if you are driving a car, you get into an accident without having your seat belt on, you are penalized both by the police as well as in the report, as well by the insurance companies. So if you take the frequency of each possible incident multiplied by its risk, this is the risk before adding the safety feature. But you subtract from it the frequency of now the new situations that you get, and you could get, in fact, more different sequences of accident than what you started with here, so that small m can be larger than n. And we'll take an example from the safety of a nuclear power station design, and then you can apply it to any other fields. So this is the frequency or the risk before adding the safety feature, and this would be the risk after we add the safety feature. And that number obviously should be positive, right? Otherwise, if it's negative, then you have increased the level of risk. So the level of risk before adding the safety feature should be obviously larger than after we add the safety feature. In that case, you call this the cost-benefit ratio. And in that, you don't use that cost-benefit ratio for one single item, like say the seat belts, but you go and try it for all different choices, not only different choices by the order at which you add the different features to your design to reduce the risk. And we'll give examples on that. So now what are the units? The units is the cost of reduction of the risk divided by the amount of risk reduction. So that becomes our delta C over delta R, not delta R over delta C. Do you see that? It's the slope, the inverse of the slope of the risk reduction curve. Now that C here in economics, people like to describe it as what they call the annualized cost of the risk reduction. How much we spend per year, annualized, to reduce the risk by a certain amount. That would be dollars spent per year. And F sub I is the frequency of the I's accident sequence without the safety feature that is being installed, events per year. And then this would be the risk after we introduce the, say, the seat belt or the airbags or any, in the case of nuclear power plants, that would be diesel generators and other safety feature. So F sub I prime is the frequency of the I's accident sequence with the safety feature installed. And R sub I would be basically the risk. Now, I am taking here as an example the risk of being exposed to radiation. When you are exposed to radiation, we call that the radiological risk. Obviously, you design different designs for nuclear power plants in such a way that if an accident occurs, you have safety features to prevent the accident from developing into a serious accident harming people. And the unit that it's used is the radiation dose. The radiation dose that we use is the number of people exposed to the radiation multiplied by the unit that is used for the radiation dose. We'll try maybe to describe that later on, but let's take it for now as REM. REM stands for radiation equivalent man. This is the dose of radiation that can cause harm to the person exposed to it. The REM is the unit in the conventional system of units. The system, the SSM International, uses the sievert as a radiation dose. So let's take that example because it has very interesting implications. And R prime sub I is the radiological sequence in person REM or person sieverts in the I sequence with the safety feature installed. So what are the units in that case? It would be dollars per year per person per REM. And this is what we are going to call the cost-benefit ratio. Before we go there, you'll find that because it's economics, the economists have established some cost for disabilities. So when people are harmed, when they're sick, even if you get COVID-19, you do not contribute to your job, and you are basically confined or in your home. So in that case, in economics, there is a cost associated with disabilities. Disabilities in that case would be people being harmed or people being sick. Now, the total social cost that we deal with in cost-benefit analysis, as I suggested, it's an economical kind of an approach, is taken as capital N is the number of individuals that are involved multiplied by the cost of one disability day. Like if you don't go to work, if you go to work, you come to lectures here, you are contributing to society, society benefits from you, and on average, say, you are contributing to society $1,000 by doing your job, whatever it is, even if you are a student studying per day. And then the economists like to take that 1 plus I to the power of T. You could see that in your classes in economics. I would be the daily interest rate. Some people call it the discount rate to the power of T. And T is the number of days that people are exposed to that disability when they cannot contribute at work to society in general. So you take it to the power of T if T is less than 6,000, and that is 6,000 days. Why is that? Anybody can guess, or from your classes in economics, what is typical of that 6,000 days? Well, take a year as 300 days and say you do not show up at work for 6,000 days. So 6,000 divided into 300 is how many years? 20 years. So economists consider that we are productive in society for only 20 years. All right. So you could see here that when T is larger than 20 years, they don't go beyond T as 6,000. They write it just as 6,000. So in that case, they consider 6,000 as, you're not contributing to society anymore. They consider you basically dead. But even if you're not dead. So it's simply sobering to think that we spent, say, like 20 years getting educated, going to school and having fun, playing basketball and football and involved in the sports and so on. And then when you graduate, you only contribute to society 20 years. That's not good enough. I hope that all of you would be contributing more like the 40 years and not just the 20 years. So this is economics, fine. You can change the numbers according to whatever arguments you can make. The National Security Council considers a value of 6,000 days to represent a fatality. Oh, that's economists have given a price to human life, which we do not accept as engineers professionally and ethically. Human life has a much higher value than that. All right, so we get here the cost-benefit ratio that we define today. And in that case, it depends on the risk against the cost of risk reduction graph. And I made the observation that it basically is a description or a realization of the law of diminishing returns in economics. We are doing some economics today. And the observation is that we cannot really reduce the risk ethically. We cannot claim that we can build any absolutely safe device. Politicians can say, oh, we want it to be absolutely safe. We tell them, well, the reality of life is that we cannot reduce the risk to zero. We can spend money, we can improve the design, but we will never reduce it to zero. This idea becomes understandable if we apply it to some actual system. And obviously, our course is being taught in nuclear engineering. So we take an actual example in the design of pressurized water reactors. This is the most common type of nuclear reactors in the world today. And to reduce the severity of accidents, even if the accident occurs, we add what we call engineered safety features. ESFs is the acronym. And one of them is what we call the emergency core cooling system. And the abbreviation for it is ECCS. Now, to add that emergency core cooling system, you'll find that nuclear power plants are equipped with diesel generators. And if you read the news very carefully, in the war in the Ukraine, the Russians have occupied the largest nuclear power stations in Europe. They have 6 units. And the connection of the plant to the grid has been basically destroyed by artillery. So they shut down 5 of the 6 units in the plant, and they have only 1 running. And that 1 running does not have input from the grid in terms of electricity if there is something that happens to the electricity from the plant itself. So they are depending on running diesel generators to provide cooling for the fuel in their fuel tank. So this is a situation that is happening today. If they fail in cooling the fuel tanks, something like at Fukushima could happen. The fuel can start boiling the water, and then it would be releasing radioactivity to the environment. That's why the Europeans are very, very, very concerned. They send United Nations delegations to try to deal with the situation. So the Europeans are in big danger if that emergency core cooling system for the last unit that is still in operation at the Zaporizhzhia plant, I think that's the name for it. All right, so the emergency core cooling system for a pressurized water reactor is a safety feature that reduces the risk of the release of radiation. We are living with it right now. The cost of operating the diesel generator per year, because we said we take the annualized cost, the cost per year is $1.5 million per year. So in our equation for the risk, the cost-benefit ratio here, we have very easily now that C, we know what is the C, and the power plant operator knows that he bought himself a diesel generator. He has to provide it with fuel, diesel fuel, and he can run it at a cost of $1.5 million per year. Now, the question is, what is the cost-benefit ratio for adding that diesel generator? Why? Because there are other safety features that you can add to a power plant, like the containment structure, for instance, or you can add the hydrogen burner in case hydrogen is produced. Hydrogen was produced and exploded in a big way in the Fukushima accident. So you go there and analyze what are the type of accidents that can happen. We'll look actually at some detail about what happened in that case. Each one of them has a risk R sub I, and it has a calculated frequency of occurrence of F sub I. And the number of possible incidents that can happen before adding our emergency core cooling system goes over the summation of that frequency here multiplied into the risk. We'll show you later how you can calculate that number, but we will calculate it later. It comes out to about 0.14 million rem of radiation, dose of radiation, multiplied into the number of persons exposed to radiation per year. Now, if you add that safety feature, you can redo the calculation. You can get different sequences of accidents, not small n. M could be larger, in fact, and then sum over all the possible accident sequences that can happen after you add the safety feature. And when you multiply that by the frequency of each type of an event, and you sum it from I equals 1 to m, you should be getting something that is less than before the adding the safety feature. If that number is larger, that safety feature is not useful. It is not producing a reduction in the risk. So now that number is written in the denominator here, 1.4 10 to the fifth, the total consequence or risk before adding the safety feature minus the risk that we calculated here after adding the safety feature. The denominator, the annualized cost of operating one of these emergency core cooling systems is $1.5 million per year. And the dose here, reduction or the risk of people being subjected to a dose of radiation if some accident happened before adding the safety feature and after adding the safety feature, the risk reduction is person, the number of people exposed to the radiation, multiplied by the dose that they get from the radiation per year. You notice here that the units cancel out here and here cancel. So you end up calculating, actually, you could see here, it's not just a subjective manner. This is a quantitative, objective way of estimating that when you add that emergency core cooling system or those diesel generators, you have a benefit ratio of $14 per person RAM. Meaning what? Meaning to reduce the dose of radiation for a person in terms of by 1 RAM, you spend $14. All right. Now, okay, fine. That is fine. But then how does it influence me in adding or not adding that safety feature? Comes the Nuclear Regulatory Commission, and it gives us some kind of a hint on how to apply that cost-benefit ratio. It tells us that if you can reduce the dose of radiation by spending $1,000 per person per 1 RAM of dose of radiation, that 14 is obviously way before 1,000. So that is a desirable feature. You should go and spend the money and add that emergency core cooling system. So in that case, it gives us a hint on how far we go on the risk reduction curve here in terms of spending money. So this is set by the laws of the land. The regulatory commissions in that case come to our help. Now I told you that risk reduction before and after adding the safety feature depends on a very detailed design of the power plant and after we add the safety feature. And this is in fact a table taken from the reactor safety study that compared what happens when we add that emergency core cooling system. So if you don't have that emergency core cooling system, remember we said ESF stands for no emergency safety feature. You can have 4 different accident sequences. We'll study those later in more detail. An accident that's designated in that reactor safety study, we called it earlier in a previous chapter, the WASH 1400. We call it accident A, accident S1, accident S2. And here is a sequence where you get a transient followed by maybe equipment failures or human errors. That's a sequence TMLB. The designers determined that that accident here has a frequency of occurring per year of 1 × 10⁻⁴. This accident 10⁻, let's see here, 6, 10⁻�3, 10⁻⁴. This accident can happen, but then the radiation is not going to be released unless the containment also structure around the power plant is breached, meaning that the steam escapes from the containment. So they have different levels of containment failure, alpha. Here you have beta and again back alpha here. And in that case, there is a significant release of radiation. So there are different levels of release of radiation. In that case, it's a very serious release of radiation, level 1. And when you take that frequency here, F sub I multiplied into the risk of that particular accident, you get F sub I, R sub I for the first accident. The second one would be F, the risk of release of radiation. You notice that all of these are the same. You are releasing radiation with a risk in terms of human, man or person. I wrote it as person rem to be politically correct, but here they're showing it as man rem. All of them would release about 80 million man rem as a radiological consequence. You add those numbers here for the risks in man rem per year for the accidents that can happen, 4 of them, as you could see here, and you get that 1.410 to the, that's the 5th power. Oh, this is what we wrote here, 1.410 to the 5th power. Now you add, and that's an interesting aspect that I would like to bring to your attention. When you add the emergency core cooling system, you do not reduce the number of sequences where accidents can occur. What you have done is that you have added complexity to the system, right? You have added the diesel generators, which can fail. And as they fail, they can generate for you not just the original sequences of accident, the A, S1, S2, and TMLB. Here they are, A1, S1, S2, TMLB. But the diesel generators themselves can fail and add many other different modes of failure shown right here. And their frequency also would be different for each one of the failure modes that initially existed, and as well as when we added the generator. But one interesting aspect that comes out of here is that even though the frequency is the same, but the release categories of the radiation is now different. It is not the most serious way that radiation is released. It's now a category 8, which is a very, very minor release of radiation. For each one of these, you take the frequency multiplied by the risk, and you add all of these possible sequences, and you come with now the total risk after adding the safety feature. Notice again that the summation can have M here, where M is larger than N. You can have more sequences because you have added complexity to the system. And that 2.510 to the 4th here is what we put in as the risk after adding the safety feature. So that's an actual example that's used in the design of nuclear power plants. And just for an explanation, what is that alpha, the beta, the gamma, and the epsilon? These are different modes of failure of the containment. If the containment structure around the power plant fails, you get different releases of radiation. For instance, the alpha is the serious one, a vessel steam explosion. That happened in the Fukushima accident in one of the reactors, apparently, because we saw on TV really a very violent explosion up to the sky. Beta is less a penetration leakage. You have cabling coming into the containment structure for control. You have pipes bringing in the feed water, and then you have pipes taking the steam out. Gamma is overpressure due to hydrogen burning. hydrogen played a major role in the Fukushima accident. Here, the epsilon did not happen here in this because the emergency core cooling system there got its functioning. But if you melt the core, like what happened again in one of the Fukushima plants, the core melts and then can interact with the concrete. The other symbols here, T1 is a loss of offsite power. You can go over all the detail. And you have the different system failure definitions. All of these are terminologies from the reactor safety study that you can, of course, review and in how that basically that structure has been built. So what we learned today is that risk can be reduced, but not to zero. There is a law of diminishing return, and that we can estimate the reduction in the risk and then set up a criterion that allows us to use or not to use the safety feature that we add to our system. That is the introduction of reducing the risk by spending a certain amount of funds in the design in general. Next time we are going to deal with the consideration of the overall system, not just a single unit, the emergency core cooling system. And I wish you all a nice weekend, and I'll be happy to answer any questions. So I'll stop sharing here.